Hey everybody, I've had a couple of questions about 7.2. So if you have your notes for 7.2, look at page number 3. It says use a calculator to find the following probabilities and make a sketch of the indicated region under the graph. Well, first let's talk about what these curves mean. This is a normally distributed curve where the average, or mu, is right in the center. Can you guess what percent of the data lives to the left of the average? That's right, half of it. Can you guess what lives to the right of it? That's right, the other half of it. So our job is to find the percent area that lives left, right, or in between various z-scores. What a z-score is it's the number of standard deviations that individual data values live away from the average. So if we have a z-score that's negative, it will be to the left of the average. This might be a z-score of -1. We can see if we found the area to the left of that z-score, it's going to be less than 50%. Whereas one standard deviation above the mean, that z-score is going to be a positive value, and we can see that more than 50% of the area is going to be the left of that z-score. So they have what's called z-score tables that gives us the area to the left of any individual z-score. If you get a z-score that's negative, again, those z-scores are to the left of your mean and will have less than 50% of the area to the left of them. Let's look at our first problem on our notes, page 3. They want the area to the left of a z-score of 1. So we want to show a graph of each. The left of the z-score of 1, we go to +1. Again, this is a z-score at the average. The z-score at the average is actually 0, kind of like a one-dimensional number line. The area to the left of a z-value of 1 would include all of this area. So we want to make a mental guess of what we think the answer is going to be before we find the answer. I know the answer is going to be bigger than 50%. I'm going to guess 58%, 70%, something bigger than that. Manually, we have to do this a long time ago, is we would look on z-table. I'm not sure if you're going to be able to see this table or not, but they give you the z-scores. This is also found in your textbook, Appendix A, pages 10 and 11. I just printed this one off by searching from Google z-score table PDF, and this was one of the first ones that popped up. We're looking for a z-score of 1, and if you look down this column, they're all negative. So you have to turn the page, you have to flip it over. And again, these z-score tables are great, but they're only for the area to the left of our z-values. Here's a z-score of 1, and then here's 1.0 is rounded to the nearest tenth, and here it is rounded to the nearest hundredth. So to use this table, we just go to the nearest tenth, to the nearest hundredth, and that's the area to the left of a z-score of 1, 84.13%, or 0.8413. I hope that makes sense for you guys. Here's how to compute it without using z-table. You didn't know I spoke French, did you? To use this table, we go into shift data, arrow over to distribution, down to normal CDF, or you can just hit select 2 from the menu and enter. When we're using normally distributed curves and there's no other data, like they don't give us the average, they don't give us the individual x values that we compare to the average, then we always choose a mean of 0. And the sigma just means that it's a normally distributed curve at 1. Scroll down one more time. This represents the lower bound. Can you guess what that number is? It looks kind of weird. That is negative infinity. So knowing that that's negative infinity, the upper bound, positive infinity. So this would be the area between negative infinity and positive infinity. What percent of the area is between negative and positive infinity? That's right, 100%. So when we press enter, the value there is 1. That's written as a probability instead of a percentage, but as a percentage, it would mean 100%. Now let's do our problem. So I scrolled down and I said, I want to solve another one. Solve again, hit it. And then we want area to the left of 1. Let's take a look at our picture. This is the area to the left of 1. So we want the area between 1 and negative infinity. The lower bound is always going to be the leftmost bound. The upper bound is the rightmost bound. So to find the area between negative infinity and 1, or the area left of 1, here's how we do it on our calculator. Again, for these normally distributed curves, the average is 0. And then the leftmost bound, or the lower bound, is negative infinity. Go ahead and keep that. That one's good. This is actually negative 1 with 99 zeros after it. So that's super duper close to negative infinity. The upper bound, the z value for the upper bound is 1. We scroll down to calculate, and we'll find the area between negative infinity and 1, or to the left of 1. 0.8413. That's exactly what we got when we used our chart. 0.8413. Let's do another one. Let's find the percent area for problem 2. We want left of a z-score of negative 3.7. The first thing I like to do is I like to graph them all. Remember, at 0, this is the average, and the z-score is 0 at the average. Plotting a point like negative 1.37, just like a one-dimensional number line, we're going to put it to the left of 0, approximately here. We want the area that's less than that. That's a fancy way of saying I want the area to the left of that z-score. So we shade that region to the left of that z-score. Old-fashioned way, we grab out our z-table and we look up negative 1.37. Here's negative 1.3 rounded to the nearest tenth, and now we have to go over to that column that's marked 07. So 07 and negative 1.307, and if I can read this right without my magnifying glass, how about right here? 0.0853. 0.0853. What this represents is 8.53% of the area lives to the left of 1.37 standard deviations from the mean. Anybody have any questions? I didn't think you would. Let's do our calculator now. Same question, solve again. This time, the average is 0. The sigma is 1 for the normally distributed curve. The lower bound is still negative infinity, but the upper bound is now negative 1.37. Make sure that you hit the negative key and not the subtract key, otherwise you'll get a syntax error. And calculate. Just like we expected, 8.53%. So far, so good? Here's where the breakdown occurs. Take a look at the next problem. Z greater than negative 1.7, Z greater than negative 1.7. A fancy way to say this is, I want the percent area or the probability of the area if you keep it as a decimal, to the right of that z-score. The other two questions were both to the left, and that's what our tables indicate. So to find the area to the right, let's graph it and highlight what we mean. To the right of negative 1.7, negative 1.7 lives there. But instead of shading left, we're going to shade to the right. And let's make an estimate of what you think that percentage is going to be. Should be bigger than 50%, right? So if you get something smaller than 50%, you knew something went haywire. All right, here we go. I can look up negative 1.7 on z-table. Negative 1.7 rounded to the nearest hundredth is this one right here, negative 1.70. That number indicates, I don't know if you can see it, but it's 0.0446. That's the area to the left, 0.0446. To find the area to the right, that's right, we know the area, the total area under these normal curves is always 1 or 100%. So we want to find this one's complement. 1 minus, plug that into your calculators and hopefully we'll all get 95.54%. Does anybody have any questions on that? Let's use our calculator to find that answer. Again, the lower bound on this one is the leftmost. The upper bound on this one is the rightmost. So let's solve another problem, solve again. Or if you're not in that mode, to get into that mode, remember hit Shift Data, Distribution, Normal CDF, oopsies, Shift Data, Distribution, Normal CDF, and you're in that mode. The average is 0. That's going to change next chapter. We'll have other values that the average won't be 0. The lower bound on this one is that boundary where z value is negative 1.7. Use the negative key and not the subtract. What's the upper bound? Positive infinity. That's why I reset this problem before I started it. But if you have something like residual from the last problem, like negative, I don't know, negative something goofy, like 1.37, I think that was the last problem that we did. You can clear that out, and all we want to put here is positive infinity. So how do you put positive infinity in there? I just hit 1 and then a bunch of zeros. Maybe not 99 zeros, but maybe 10 zeros, and that will indicate positive infinity, and then you can calculate based on that. The area to the right of negative 1.57. I'm sorry, negative 1.7. Voila. Last problem real quick. The area between these two z-scores. This z value is to the left of the average. This z-score is to the right. So if we pictorially show this on our normally distributed curve, it would look something like this. Using the old-fashioned technique, we would have to find the area to the left, or this white space. Then we would have to find the area to the left of this one, the whole thing, and subtract them. Find the area to the left of 0.89. To do that using z-table, we go to 0.89, 0.8, and then to the nearest hundredth, all the way over 0.8, 9. It's hard for you to see, hard for me to see as well. And we get 0.8133. So the area to the left of this score is 0.8133. Does that make sense that it's bigger than 50%? That's all of this area. Now we subtract off the white space, or this zone right in here, by looking it up. And when we look up negative 0.52 as a z-score, negative 0.5, where are you? Right there? 2, 0.50, 0.51, 0.52. And that number is 0.3015. So the area to the left, 0.3015. All we need to do is subtract those areas and we've got our made. So the area, 0.8133 minus 0.3015 is 0.5118. 0.5118. Slightly different than our filled in notes because the filled in notes used our calculator and didn't round. The bad thing about using these old-fashioned z-score tables is they round them to the nearest thousandth on both cases, and then you subtract. Last time, guys, let's use our calculator, clear that out, shift data, distribution, normal CDF, accept the defaults until next chapter. This time the lower bound is the value that's the negative one, negative 0.52, and the upper bound 0.89. Calculate that, and that's what they got on the guided notes. 0.5117 rounded to the nearest 10,000th. Guys, I hope this was helpful. Sorry I'm so long-winded on these. Make sure you do a couple of problems a day, even throughout the spring break. Again, chapter 7 and chapter 8, when we get back to school, those are the ones we're going to be discussing, and we'll take a test on those. If you have any other questions, please email me, and I'll try to get back to you as soon as I possibly can, even through next week. Stay healthy, everybody. Talk to you soon.